Hello, this is Dr. Fallon. In this module, I want to talk about Six Sigma. Specifically, I'll talk about definition of Six Sigma quality, history of Six Sigma at GE, and then go over a case study of application of Six Sigma methodology. So what is Six Sigma? Sigma is the Greek symbol representing a standard deviation in measuring variation of a process. So Six Sigma simply means 6 standard deviation in a statistical context. Six Sigma is also a measure of quality by reducing the variation of the process to the extent that all output of the process falls within 12 standard deviation and essentially be error-free. As a methodology, it is also a quality improvement tool for breakthrough improvement in any process. Sigma can also become called a management program when organization adopts Six Sigma as the core of the TQM system. So those are various ways of people looking at Six Sigma in terms of its definition and use. So what is Six Sigma quality? Every process has some inherent variation. When the variation of the process exceeds its allowable tolerance, whether it is required by design or specified by the customer, then the output of the process is unacceptable. It could be rejected, it could be scrapped, or it could be reworked to make it acceptable. So as a measure of quality, then Six Sigma represents a defect-free process. In other words, we're reducing the variation of the process to the extent that all its outputs are acceptable. And in the industry, there is a numerical standard for Six Sigma process that's 3.4 defects per million opportunity for output called DPMO. In the past, we have measured quality in terms of percentages or percent good. As we reduce process variation under Six Sigma concept, then we're moving to a higher level of measurement and measuring quality in terms of the Sigma level or ppm, number of defects per million opportunity. So this table actually shows the process quality in terms of the Sigma level, the number of defects per million opportunity at that Sigma level, and what's the corresponding percentage of the process producing good output. So if we start at the 2 Sigma level, which correspond to a 69% good output, not a very high quality, the process can produce over 308,000 defects per million opportunities. As the process is improved and variation is reduced, moving to 3 Sigma and 4 Sigma and 5 Sigma, we can see at 5 Sigma the number of defective output per million is reduced to 233, and that's corresponding to 99.97% good output. At 6 Sigma level, as we defined before, the ppm is dropped to 3.4, which is correspond to 99.999 in terms of good output. So this has become more of a standard in the industry, referring to Sigma level as well as the ppm when we're measuring output of a process that has been going through Six Sigma improvement. So what is a Six Sigma process? A Six Sigma process implies that the process variation has been reduced so much that a spread of 12 standard deviations, 6 standard deviations on each side, of the mean falls within the range of the specification limit. In other words, all output of the process is acceptable and meets the quality requirements. So in defining Six Sigma process, however, Motorola allocated 1.5 sigma on each side of the mean for a long-term shift in the mean of the process. Remember, this was developed in a manufacturing environment where machinery and equipment over time, the mean value of the process could shift, and so they made an allowance of 1.5 on each side of the mean for that before tackling the variation. And so a Six Sigma process is actually a true 4.5 sigma process. I've shown that here. So if we have a specification limit, a lower specification limit to upper specification limit, and we allow 1.5 sigma on each side of the mean for the shift in mean, then 4.5 sigma on each side represent the variation of that process, and that will produce 3.4 parts per million, as we discussed before. So while a standard industry Six Sigma process, as I pointed out, produces 3.4 parts per million defective output, a true Six Sigma process, the number of defects is reduced significantly more to 0.002 parts per million. I've depicted that in this chart here, where we're not making any allowance for the shift in mean, and so 6 standard deviation of variation on the left side of the mean and 6 standard deviation variation on the right hand side of the mean falls still within the specification limit, and so the output is totally or almost flawless all the time, and the tail of the process on each side can only produce 0.001 parts per million, something that we probably cannot visualize in real life, how often that could happen. And so in such a process, if the process mean and specification limit are centered on each other, then the process capability is actually equal to 2. So as I've shown in here, process CP equal to CPK equal to upper specification limit minus lower specification limit divided by 6 sigma will be equal to 2, because this is 12 sigma range divided by 6 sigma. So to appreciate the difference in sigma performance visually, it's important to look at these two charts. On the left, I have a process that says performing at 2 sigma, which means that the specification limit here, the range of a specification limit, covers 2 sigma variation on each side of the mean. And so the shaded area on both ends of the distribution produces output that are not acceptable, and that correspond for a 2 sigma process, as we showed before. It's over 308,000 defects per million. However, if we improve this process to move it up to 6 sigma, here I've shown again the specification limit the same as before, but the process standard deviation has been reduced so much that 6 standard deviation on each side of the mean actually falls within the specification limit, and that corresponds again, as we showed in the previous chart. The level of defects will be 0.002 per part per million on combination of both tail of the distribution. And so we can see that it requires a significant amount of effort to reduce the variation from 2 sigma to 6 sigma to get essentially flawless output. Now, the effect of off-centering that Motorola allowed in defining this Six Sigma program or quality is depicted in this chart. If you don't have any off-centering, as I showed in the previous chart, the part per million defects is only 0.002. However, if we allow half a sigma for off-centering, that part per million increases to 0.019. If we allow 1 sigma for off-centering, that goes to 0.39. At 1.5, which is the standard for Six Sigma process, then the number of defects are 3.4 parts per million. If Motorola would have chosen 2 sigma for off-centering, then today we will be talking about the Six Sigma process that can produce 32 defects per million. But they decided to pick 1.5. That may look arbitrary, but it was essentially based on their experience in manufacturing process. And so once they adopted 1.5 as the standard, it was adopted by the industry. And now when we talk about Six Sigma, no matter what the process, whether it's manufacturing or services, we are measuring those processes on the same basis of 3.4 parts per million defective. Now, there may be a myth about Six Sigma. People may think it is too complicated or it's only for manufacturing. It doesn't apply to services. That's not really true. Six Sigma, while it evolved and from manufacturing, it can be applied to any process in any organization. And to illustrate that, I picked an example from billing process. Billing is a process that almost every organization has. So let's say that I selected 1,000 issued bills randomly and inspected them for defects, and find that 125 of them had some sort of error, maybe wrong amount or wrong date or wrong address, something that resulted in rejection of the bill. So with that data, the percent good output from our billing process is 875 over 1,000, which is 87.5. So the sigma quality, then, to calculate that, we take the 87.5 as the probability of producing good output, and then find what is the z-value for that probability. So if we look at the normal distribution or a z-score table, you look within the cell in terms of applying 0.875 as a probability, and you find out that the z-value for that is 1.15. And so now we have to add, it's true that it's a billing process, but we still have to add the 1.5 shift in the center. That's part of the definition of the Six Sigma. So this process is performing at 2.6 sigma. Now, so you could see that calculating the sigma performance of a process, actually of any process, is relatively simple. All we need is to have enough data to have an assessment of the percentage of the time that the output is good. So anybody can really calculate the performance of his or her own process in terms of the sigma performance using the approach I illustrated here. There are also sigma calculators on the web and tables, which built this 1.5 into the normal distribution. And so when you put in the number of defects and the sample size, they will give you the sigma level. Now, the good thing about sigma performance is that it's a consistent measure now that we can compare processes to processes. It's just like apple to apple. So if the billing process is performing at 2.65 and we look at, let's say, purchasing process, and that's 3.5, and you decide that we really need to improve the billing process, then we can not only comparing to those other processes, but also set objectives to improve this process and finding countermeasures to things that creates billing error and improving the process. And each time we improve the process, the Sigma level would go up. Now, not necessarily go to Six Sigma. It will probably take a significant amount of effort to get to that level, but any improvement in the Sigma level corresponds to a significant reduction in the defects and errors. This is actually the table. This Excel sheet is available in the course content with detailed level of the Z-score. And so when I was looking for the Z value for the billing error, then I came actually at this is the value. It was 0.8749, almost equal to 0.875, which corresponded to 1.15 that I use in my calculation. So let's talk about Six Sigma program. Now, Six Sigma, as I describe it, is a tool for quality improvement or process improvement. When it becomes a corporate-wide initiative and it becomes the core of the quality management, then normally it's referred to it as a Six Sigma program. Now, in that context, then the quality improvement projects normally follow Six Sigma methodology, and every project is qualified and follow the various steps of the methodology, and I will be talking about it. Six Sigma methodology then become the key element or key tool under the umbrella of TQM. So now let me talk a little bit about the history of Six Sigma. Motorola actually has been a pioneer in quality management. In 1981, they launched a 10 in 5 initiative that was aimed to improve the quality of its key products by a factor of 10 in 5 years. By 1986, they actually achieved that goal, and so the company then decided that they want to go for perfection, and that's when the Six Sigma initiative was initiated in early 1987, and Motorola, with its culture of quality and under the Six Sigma program, was able to actually achieve and get one of the first Malcolm Baldrige Quality Award. And so, but between 1988, when Motorola won the award and publicized its Six Sigma program, and shared that with other companies, it took a while before the program really caught up with the industry. One of the companies that extensively used Six Sigma was Allied Signal, which is now part of Honeywell. And Allied Signal claimed that between 1994, when they started using Six Sigma, and 1998, the savings from the program, the cost saving, was about $1.2 billion. So Larry Bossidy, who was the CEO of Allied Signal, encouraged Jack Welch, who was the CEO of General Electric, to try Six Sigma, because he had this experience in terms of the benefit both in quality and cost. And so that's how GE got into Six Sigma, and the success of GE with Six Sigma really led to the growth of Six Sigma program globally. And today many companies do have Six Sigma initiative within their quality management programs. So a little bit more about the GE Six Sigma program. GE's quality was very good. Back then, they have been following a number of different initiatives in quality management. In 1995, then the company set this stretch goal to reach Six Sigma quality by the year 2000. Now, at the start of the program, GE's quality was around 3.2. Now, GE is a large corporation. It's a global corporation with a variety of products and services. Some of the products, such as jet engine, even at that time, was at Six Sigma or better, given whether jet engines are used. But they also had other products like refrigerator, toasters, microwave oven, dishwasher that were not at Six Sigma. So the idea here was to drive quality from that average of 3.2 Sigma, which corresponded to 35,000 parts per million defects, to Six Sigma and reducing defects to 3.4 part per million. So the initiative was corporate-wide and driven by Jack Welch. Now, as the program was deployed and the company achieved benefits from the program, the net benefit grew year by year, and by 1999, GE reported $1.4 billion net benefit from its Six Sigma program. That's the last year that they actually reported that data. Now, as I pointed out, Jack Welch, the CEO, was behind the program, and in GE at the time, promotion and executive bonuses were actually linked to their performance on Six Sigma program. Now, here's a quote from a letter that Jack Welch sent to employees in May of 1996, which I've quoted here as saying, "This is the most important initiative this company has ever undertaken. It will fundamentally change our company forever." So as long as he was the CEO, he drove quality improvement and Six Sigma program throughout the GE. Now, what is Six Sigma methodology? Now, as General Electric adopted Six Sigma as part of its program, they also standardized the methodology for using Six Sigma on project. That's what we call DMIC. That's a variation of what was known as Deming cycle of Plan, Do, Check, Act. So General Electric took and added a front-end phase or step to the process, calling it define, and then going to measure, analyze, improve, and control. And just as we pointed out that the Six Sigma was a standardized Motorola, the methodology for applying Six Sigma was also standardized by GE, and this is now being used globally when people talk about Six Sigma methodology, DMMIC. So let's talk a little bit about what these steps are. The first step, the define step, was to scope the program and do some initial assessment of whether or not it's worthwhile to pursue this project. Is it important to our customer, and does it have enough benefit to the corporation? Now, if we pass that measure or that threshold, then the project was adopted and launched, normally with a cross-functional team led by a black belt. That's actually an example of what GE was using, and other companies followed the same. Now, once we have that finish the define phase, you get into the measure phase here, where the team now define the processes, do a process map, define the metrics, define what is understandable or as defects as the performance measure, and then collect data. If the data is not available, collect specific data to baseline the process and its performance at the start of the project. And then we get into the analyze phase, where the data then is dissected and analyzed using statistical tools, Pareto chart, root cause analysis, and other tools, control chart, to find out what is causing the variation in the process and producing defects. With that, then identifying the most likely root causes that need to be addressed in order to improve the process and meet the project objectives. So that with that phase, then we'll get into the improve phase, where now understanding what the key root causes of the defects and variation is, the project team can use brainstorming or other technical tools to find out how to counter those defects and remove those defects from the process, reducing process variation to improve process output. Then once they identified what those countermeasures are, normally what they do is you pilot that and try to see whether actually has the impact that was intended for. And with that validation, then the improvement can be deployed to the entire process or entire organization. And then we get to the final phase, which is the control phase. This is to verify that that improvement has actually achieved the project objectives and put in mechanisms so that it can be sustained over time. So those are the steps. So each now, depending on the complexity of the project, sometimes the tools that are used are more complex, and sometimes they are not as complex as we think it could be or should be. But they all follow these 5 steps. So Six Sigma impact, when process varies, as I talked about it before, we're talking about in Six Sigma, we're talking about variation, process variation, and producing defects. So when process variation exceeds that specification limit, it creates defect, and defects essentially has a negative impact on financials, on customer commitments, and could result in delays of the project and so forth. So there is a negative impact when we have significant process variation. And reducing that process variation reduces the variation and eliminates the defect, which result in significant positive impact on the process, on the organization financially, and most likely, oftentimes, on customer satisfaction. So Six Sigma projects are normally, this is how GE started, normally are led by a black belt who has experience in Six Sigma project, is well versed in the methodology and the statistical analysis, and kind of following those 5 steps to completion and achieving the intended results. So, but not every process needs to perform at Six Sigma. So as for example, I showed that, although I made that billing process, made up those numbers, the process was at 2.65, and let's say that we make some improvement in the process, could get to 3.5, and may decide that that's good enough, because the more you're going to reduce the variation of the process, it means there's significant more effort required to do that. And there's always a trade-off in any business decision that we have to make. And so not every processes will be at Six Sigma, but there are processes that people's lives is dependent on it, like I pointed out, the jet engines in jet plane, and some medical equipment and so forth that need to be at Six Sigma because of its importance and its criticality for people. So the continuous process improvement drives the Sigma level from whatever it is to higher level and higher level as we go through the cycle, and then the company can decide what is good enough, or continue another cycle for further improvement in the Sigma level. So that's a little bit about the whole concept and application of the Six Sigma in terms of the methodology and use, and how do we calculate the Six Sigma. Now let me go through a real case example to illustrate how the Six Sigma methodology is applied. Now, this is a application of Six Sigma to a large call center, a real case study. The information that I have here is really a statement by the publisher that the paper was published in 2010, and its content can be used for educational purposes without permission and without charge, and that's what I'm doing in this module. The paper identifies a few key issues with call center processes that impacts the quality and customer satisfaction. One of those is lost call. When the calls are coming in, if the caller runs into busy lines, or if he's holding so much and then decide to drop the line, that's a good thing for the organization, and it leads to customer dissatisfaction. That's one of the elements of customer dissatisfaction. Also, if the customer has to hold the line and wait online for a long time, that's also not a good thing, and it is a cause of customer dissatisfaction. Another issue they identified was the not resolving a call in the first attempt. So in a call center where people have issues, the customer calls in and they expect their problem to be resolved while they're on the line. And if that's not done and they either get passed to another department or they have to call back, that's not a good thing from customer satisfaction and also from the corporate perspective. And the more customers have to call back, that actually inflates the number of calls and result into more demand for staff and equipment. So these are typical issues with the call center. This case study focus on not resolving calls in the first attempt. So the project was initiated to improve customer satisfaction, and in the problem statement, the notion was that the percentage of the calls that are coming in are not resolved on the first attempt, and that results to rework and customer satisfaction, and they wanted to improve that. And so a cross-functional team was created and was led by a black belt to look at that call ratio, the ratio of unresolved call to the total call, and the goal was to use Six Sigma methodology to improve that ratio. So now let's go through the 5 phases of the methodology. So the team, in the define phase, the team created a process map. They agreed on the scope, they created a process map, and agreed on the definition of defect. In the definition of defect, a query that was not completely resolved the first time, forcing the customer to call back, and so creating unnecessary work and lowering customer satisfaction, that was considered to be a defect. And so when is a call not fully resolved? Is when the call, at the end of the call, is still open in their customer relationship management system, or was escalated to other department or passed on to another group. That was the definition of defect in that context. So now with that, then they entered into the measure phase, and in this phase then they established the key measure of the performance. As we discussed, that was a ratio of the unresolved call, and they took a random sample of calls to baseline the process and creating a process map and calculating the baseline performance. Now I have shown that in the table here, the sample data they selected was 91,134 calls, of which 10,769 was not resolved in the first attempt, and that led to an 11.82% of those calls with the DPMI defect per million opportunity of 118,167. That corresponds to a sigma quality of 2.684, and I've shown here to get that number. You look at the z-value for the percentage of the call that were good, 0.8818, and you add 1.5 to it, and that result 2.684. So they get into the analyze phase. Here they took that data with the number of calls that would not resolve the first and tried to figure out what was the problems, and they dissected the data and used Pareto chart to identify the more common issues with those calls, and they created this Pareto chart. Since the information is proprietary to the company, they did not specifically set what these categories of problems were, but they identified them as A, B, C, and the first two categories where they focus on causes about 70% of those unresolved calls. So then went into root cause analysis to find out what is causing these issues and finding out the root cause of the problems. Then we get into the improve phase. So knowing what the root causes are, or the primary root cause of the problem was, then they focus on the process map. They walk through the process and they will identify a couple of specific things for quick action that can improve the process, and then did additional brainstorming and identified a couple of additional measures they could take. So they were focused on 4 measures that could improve this call ratio. And so the first tested those measures in a subsection of the call center to see whether or not this actually is effective, and then once validated that, then they look at the overall call center to see whether they can validate that the improvement for the whole call center, and they once they did that, then they were ready to move to deployment and next phase. So in the improve phase, when they collected the another sample data to see whether or not they have actually achieved the improvement, again, this was another random sample, 27,385 called, out of which 2,315 now this time was defective, which is corresponding to a percentage of 8.45. and defect per million opportunity of 84,535. Again, the sigma quality now this time went up to 2.875. So based on the this pilot study result, the improvement action reduced the percentage of the unresolved first time call from 11.8 to 8.45, and over 3% reduction in the unresolved first calls. So this was considered satisfactory. Again, as I pointed out, not every process has to be go to Six Sigma. They considered that these actions were good enough at this point, and so they wanted to roll it out to the entire call center. And that brings us to the control phase, where they documented those actions in a control plan, which was then handed over to the process owner to fully deploy and make sure that it is sustained over time. They also, with that, they also look at the 3% reduction in the call, that improvement they have achieved, and based on the total volume of the call coming in to the call center, that corresponds to 36,000 fewer calls as a result of the improvement, because they had an estimate of 1.2 million calls coming in annually. And based on that reduction in the number of calls coming in, they estimated that that leads to $200,000 annual saving, because some people, some staff, and some equipment, telecommunication equipment, will be freed up as a result of the demand for less call coming in. So that's again, you can see how systematically in that case study people went through the various steps, used the data, did the analysis, they found root causes, they came out with the countermeasure, tested those, and then deployed them to the organization. And also the last step was very important to show that it reduced the total call and also had savings for the organization. So with that, I'm just going to summarize what we covered in this module. I talk about the concept in Six Sigma and various definitions. What's the industry standard for Six Sigma quality. I showed how to calculate Six Sigma performance of any process. I'll talk a little bit about the history and evolution of Six Sigma both in Motorola and GE, and then went through step by step through this case study of application of the Six Sigma. With that, thank you for watching.